So we're going to go through chi-square. There's two different types of chi-squares that we will be learning. One of them is goodness of fit, and the other is test for independence. But let's just kind of talk about first, like why we would use chi-square. So specifically, chi-square is used for discrete data or categorical data. So in your previous chapters of inferential testing, we were using, for the dependent variable, we were using interval or ratio measurement scales for the data, which is continuous data. These are called parametric tests because we're testing hypotheses about the parameters in a population. We're inferring that our sample will look a certain way within the population. It generalizes to the population. And this is because we're able to estimate parameters in the population. We have actual normal distributions because we have continuous data. So what we're dealing with now with chi-square tests is what's called non-parametric tests, because we cannot infer from a chi-square test about the population. We can just state this is what we're seeing in the sample, and we can look at basically what our observed frequencies are and what we would compare to what we would expect to see. So with the chi-square test, it's specifically looking at discrete data with frequencies of occurrences. So this will look more obvious when we start collecting the data and looking at it. So with the parametric test is a little review of what we mean by continuous data. Is any data that the dependent variable is measured with an interval or ratio scale. So there could be an infinite amount of numbers between every major increment. So there could be 1.33333, 1.999. So this is this infinite amount of data. So we have intelligence tests are on the interval scale because they the 0 does not mean an absence of intelligence. It's just a placeholder. And then ratio scale, things like physiological measures like weight and time. Those things, the starting points, measurement starts at 0 and goes up. Both interval measurement scales and ratio scales are what we measure with parametric tests, because we can actually create normal distributions with these. But with the non-parametric test, we're talking about using ordinal data or nominal data. So that ordinal measurement scale is that ranking, like low, medium, and high. They're just categories. And then nominal data, like you're either Republican, Democrat, or independent. And so all we're looking at is the frequencies that it occurs in these categories. So if I said, how confident do you feel in your ability to calculate statistics? And I said, here's your choices: low ability, medium ability, high ability. You're going to choose one of those categories, and I'm just going to, it's basically a tally mark. Okay, I have 5 people who have a high ability, I have 5 people with a medium ability, I have 5 people with a low ability. All it is a frequency of occurrences. And then same with nominal scale. It's the same thing as if I was asking you what your political affiliation was and just check marking how many people I have in each of those categories. So it's just categories and then frequencies of occurrences within those categories. So we're going to learn 2 different types of parametric tests. These are really what I call baby statistics. So you've done all the hard work up to this point. This is the easy stuff here. So the nice part is you get to end on an easy note at the end of the semester. So let's look at our 2 different types of non-parametric tests, and we'll start with the chi-square goodness of fit, and then we'll move into the chi-square test for independence. So with the chi-square goodness of fit, it is just looking at the frequencies between the observed frequencies and the expected frequencies. So the expected frequencies are basically our null hypothesis. So if I asked, what, if I said in this class, I want to see if there is a difference in how many people feel as if they can calculate statistics appropriately, like this, previous question, low ability, medium ability, high ability. I had to get a trigger of memory. So if I threw out that question, I would say, well, I do think that maybe I have more students that actually have a high ability at this point in the semester than I do a low ability, because I'm an optimist and that's the way I think. So, but that would be my alternative hypothesis. My null would be there's no difference between the ability of students to calculate statistics, meaning that I'm looking at the low ability, medium ability, and high ability as being equivalent, basically the same amount in each. So with those notations, now we have the actual chi-square, which is that x squared, which is our notation for chi-square. And then now we have these notations f of O and f of E. So you've already seen F before. It was when we did grouped frequencies way back, and I think it was chapter 2. And it's just a frequency. But now we have observed frequencies and expected frequencies. So our chi-square equation is very simplistic. There's no more sums of squares at this point, which is very nice. But so our chi-square, if you'll notice, the difference between the observed and expected frequencies are in the numerator here, and they're squared. So no matter what, our chi-square is going to be a positive number. So basically, our distribution for chi-square looks like this. So our critical region is always over here, because chi-square is always going to be a positive number, because we're squaring those differences. So let's take a look at an example of what we would see if we were given a simple chi-square goodness of fit. So let's say we have this alternative hypothesis that there will be a significant difference in the frequencies of observed eye colors. And so we have people in blue eyes category, brown eyes category, green eyes category, and other, maybe rainbow eyes, as you can see. And so if you can see, these are the F of O. These are what we have in our sample. So if you look, if you add this up, 12 plus 21 plus 3 plus 4 is 40. That's where we're getting our N equals 40. There were 40 participants. So if we have our null hypothesis, our null would basically be there will not be a significant difference. So, not. That's the key. So if there will not be a significant difference in frequencies of observed eye colors, then we need to figure out, okay, well, what are our expected frequencies? But before we do that, let's look at how we set up our criteria, which is the step 2. So step 1 is the alternative, well, the hypotheses, the null and the alternative hypotheses. And then step 2 is the critical value. So the critical value is found using degrees of freedom, but degrees of freedom is calculated by categories now. So if you look, it's K minus 1. And you should be familiar with K just based off of ANOVA. K is just the number of groups the independent variable has, or the number of categories the quasi-independent variable has. In this case, we have 4 categories, blue, brown, green, and other, minus 1, which equals 3. Okay, so our degrees of freedom is 3. And if we're using alpha 0.01, we're going to look at the back of our textbook, and this is the very last table at the very back of the appendix in your textbook. And you're going to just look up the degrees of freedom of 3, and then you're going to look at 0.05. It's very simplistic, very, very simplistic. So for a level of significance for criteria of 0.05, it's 7.81. So basically is what we're looking at is, okay, our test is going to be significant if our test statistic falls beyond 7.1, 7.81. And so this is our critical value, 7.81. So anything beyond that is significant. So here's how we would find those expected frequencies. So in this case, we're just saying basically that there is not going to be a difference in the frequencies. There's going to be no difference. So what we want to do is we want to split our frequencies up equally. So is what we want to do basically is do proportion times n. Now, to me, the easiest way to do this is just take n, whatever your n is, and divide it by how many categories there are. So I'm going to divide n by 4, right? So if you recall, n is 40 divided by 4. Oops, not 40, but 4. Okay, so that means our expected frequency equals 10 in each of those categories. So when it says proportion, is what it's saying is you want to find the proportion for this cell relative to the other cells, the proportion, which is 1 out of 4 cells. So ultimately it's 1/4 times n for each of the cells, which is the same thing as n divided by how many cells you have if you're distributing them equally. So that means our expected frequencies are 10 for each cell. So as what I do is I set this up to where I have my observed frequencies on one row, my expected frequencies in the other, and then I can easily just calculate my chi-square calculations. So if we recall, chi-square equals the sum of the observed frequencies minus the expected frequencies squared divided by the expected frequencies. Okay, so we can easily calculate those. So here's what it looks like. We're going to focus on cell 1. Okay, cell 1 of observed frequencies is 12. It has an expected frequency of 10. So we do 12 minus 10 squared divided by 10, and then we're going to focus on the next observed frequency. So for however many categories you have or however many observed frequencies you have, that's how many little chi-square equations you should have. So here's 1, 2, 3, 4. So however many observed frequencies for each cell. Then we add up our obtained statistics. Be careful when you're calculating these because that can be tricky with all the decimals and then the rounding and the parentheses and all that. So just be real careful. And remember, you're always going to have a positive numbers. And we got a chi-square obtained of 21. That's pretty big. And if you recall back here, we're supposed to be 7.81 or larger. Well, our obtained statistic was 21. So it's definitely significant. There is definitely a significance in the differences in observed frequencies. So now we're done. I mean, it's that simple. The chi-square goodness of fit is very, very simple. There's no effect size because you can just look at the data. And is what I usually do is summarize kind of what the pattern was. So for this, I put the proportion for eye color showed there was a significant difference. Or you could say the frequency for categories of eye color showed there was a significant difference, whichever you prefer. Then we have our chi-square. We give our degrees of freedom and we give the total sample size, how many people participated. So it's 3, n equals 40. And it could be capital N or lowercase n, either way. And then we give our obtained test statistic And because it was significant, P is less than 0.05. And this is where I add on a little follow-up sentence. Instead of calculating an effect size, I just basically say what was going on. So if you look back, blue eyes, brown eyes, green eyes, other, you could see like, okay, brown eyes were observed the most, 21, and green eyes were observed the least. So that's all I did, was just kind of give it an idea of what was going on, what kind of patterns was occurring. So that is the simplest analysis we will use. And we can't even state the proportion for eye color in the population per se, because we don't have normal distributions. We don't have continuous data to make that kind of statement. It's just what's going on in those samples. So then we have chi-square test for independence. So chi-square test for independence is also a non-parametric test, but now we're dealing with two independent variables or quasi-independent variables. So with the goodness of fit, you have one independent variable. So like for the last example, it was just eye color, categories of eye color. So there was 4 categories for eye color. But what if we said, is there a difference in the frequencies of eye color related to gender? So then now you have males versus females plus the 4 categories of eye colors. That's a second variable. So when you do a chi-square test for independence, we're talking about 2 categorical variables that are independent, and we're just looking at the frequencies of those. And it's basically looking at a relationship between those 2 variables. Is there a relationship between eye color and gender? Frequency of eye color and gender. So here is an example. So we have number of children. So we have 2 different categories, 2 or less children or more than 2 children. And then it looks like we're looking at education, college education or high school only education. So we're looking at, is there a relationship between education level and number of children that families have probably? So our alternative hypothesis is that there will be a significant relationship between number of children and parent education. So if you notice, there's numbers, and I have these cells numbered 1, 2, 3, and 4. These are our observed frequencies. So 53 college-educated people had 2 or less children. 22 college-educated people had more than 2 children. 37 high school education people had 2 or less, and then 38 high school education only individuals had more than 2 children. So these are our observed frequencies. So now we have to come up with our expected frequencies, but we also have to come up with our criteria. So let's look at our criteria first. That's step 2, setting up our criteria, because we'll never know whether something is significant if we don't have our criteria set up appropriately. So again, the equation is exactly the same as with the goodness of fit. The only difference is how we obtain the F of E, the frequency of expected values. That's the only difference. And then the getting the criteria is a little bit different, because now we have categories for different variables. So basically what we want to do is get our degrees of freedom for how many categories are in each of the variables. So K is just the numbers of categories for each variable. So for education, there's 2 categories. Okay, so we're going to go 2 minus 1 for education. And then for number of children, there's 2 categories. So we're going to go 2 minus 1 for that. So luckily for us, we just have a 2 by 2. So when we multiply these together, if you'll notice, it's 2 minus 1 times 2 minus 1 here, our degrees of freedom is 1. So if you look at the table at the back of your textbook, alpha 0.05, your critical value is 3.841. And so now we know, okay, anything more than 3.841 is significant. So now we can start calculating, but first we have to find our expected frequencies. And that's where it gets a little bit trickier with our chi-square test for independence. So, and this is one of the reasons why I number the cells, so it keeps you on track of which cell you're working with. So here's how we get our expected frequencies. So is what we do is we take the frequency of the column total times the frequency of the row total and divide by the total number of frequencies. So frequency column times frequency row divided by n. So if you're like, what do you mean by frequency column and frequency row? It's not the observed frequencies. So if you'll look, we're going to add these up. So 53, ignore the ones in the red, 53 is our observed in this category and 22 is our observed in this category. 53 plus 22 is 75. So that's our frequency row for these. Then 37 plus 38 is 75. So again, another frequency row. Then if we look here, 2 or less, 53 plus 37 is 90. That basically is our frequency columns. These are 22 plus 38 is 60. So those are our frequency columns. So what we just want to do is for each cell line up its row and column totals. So for cell number 1, we're going to look over here, boom, and we're going to look down here, boom, line them up. So 75 times 90, because remember 75 times 90 in the column and row frequencies, divided by our total sample size is 150. So if you add up 75 and 75, that's 150. But if you add up 90 plus 60, it's 150. So that's how many people participated. So then that's why I kind of organize these. So for cell 1, I did 90 times 75 divided by 150. That expected frequency is 45. Cell 2, 60 times 75 divided by 150. That expected frequency is 30. Cell 3 is repetitive, and cell 4 is repetitive. So obviously with a 2 by 2, you're going to have repetitive numbers, but when you start getting into 2 by 3s, 3 by 5s, then you have less repetition, so you really want to keep track of things carefully. So now we have our expected frequencies, and we can just do exactly what we've done before. Now, we have 4 cells and 4 observed frequencies, so we're going to have 4 chi-square equations that we're adding together. So if you look here, we have the chi-square equation for cell 1, 53, the observed, minus the expected, 45, squared divided by 45, right? So that's for cell 1, cell 2, cell 3, cell 4, right? And then we add those together and we get 7.07. So if you recall, our criteria was 3.841. So we have significance because if we look here, here's 3.841 is over here. 7.07 is way over here. So that's significant. So now we do need to calculate an effect size, because with chi-square test for independence, we're talking about a relationship. We can't just look at it and start easily coming up with patterns. We just need to say that there is a significant relationship between education and number of children. And then we need to provide an effect size with it, just like we did in the past. And there's 2 different types of effect sizes. There's phi coefficient and there's Kramer's V. So whenever we have a 2 by 2 equation, which is what we just had, so 2 categories for each of the independent variables, we're going to use the phi coefficient. And so this is our chi-square, so that 7.07, right? 7.07 divided by 150, right? Wasn't it 150? Yeah, 150. and then we're going to take the square root. Now remember, it's not 7.07 squared because that is the notation for chi-square. Now, for larger matrices, so like a 2 by 3, a 3 by 5, etc., we use Cramer's V. Now this is where it can get complicated because the Cramer's V and the phi coefficient are going to be the same calculation if you are using a 2 by 3. It's going to be the same value if you have a 2 by 3 or a 2 by 2. Because is what you do is this, you're going to take your sample size and times it by the smallest degree of freedom. Well, if you have a 2 by 3, so you have 2 categories here, but 3 categories here. So you see the 2 by 3. Well, here is 2 minus 1 degrees of freedom. This is 3 minus 1. So we're going to use the smaller degrees of freedom. That means this would be multiplied by 1, the sample size would be, which means this Cramer's V would equal the same as the phi coefficient. But it's inappropriate to report a phi coefficient if you have anything larger than a 2 by 3. Or anything larger than a 2 by 2. So a 2 by 3 or larger, you should be reporting a Cramer's V. Now then we could be adding, you know, okay, now we have maybe a 3 by 6. Well, now we have 3 minus 1 here. So we would be multiplying by 2. So that would change things up. So just know that for a 2 by 2, you use the phi coefficient. For anything larger than a 2 by 2, you're going to use Cramer's V specifically. So here's our results for that test for independence. We're just going to state that it showed a significant relationship between number of children and parents' education. Again, chi-square, in parentheses, the degrees of freedom we use to look up our critical value, sample size, our obtained test statistic, because it was significant, p is less than 0.05, and because this was a 2 by 2, phi coefficient equals 0.22. Okay, so again, in this calculation, make sure you're taking the square root and make sure that you're just using the obtained test statistic and that numerator. So you just learned chi-square test for independence. Very, very simple. These are both chi-square tests are both very, very simple tests, but the distinction is that you're dealing with categories and just frequencies of occurrences in the categories. So that really is the big clue to knowing when chi-square is appropriate. So hopefully this helps. I'll be posting this in your objectives. And if you have any questions or want some clarification, please don't hesitate to email me or come see me during Cranium Cafe hours. Thank you.